A decade ago, a massive tsunami slammed into Japan. I was based in Japan as the ABC correspondent when the tsunami hit. The scale of suffering and destruction was truly devastating.
The tidal wave devastated much of Japan in 2011, with over 20,000 dead and hundreds of thousands of homes destroyed. The world was shocked by the magnitude of the event, which caused Japan to construct an enormous tsunami defense system that covered 250 miles of its eastern coastline.
In its aftermath, the government pledged to build massive seawalls to protect communities from future tsunamis. But many say the walls designed to protect their communities.
In order to build towering, nearly 50-foot tall walls that can withstand the impact of millions of tons of ocean water, Japan has had to mobilize tens of thousands of engineers, deploy some of the best machinery available, and create precise construction processes for every millimeter of the walls. However, one big question is this great concrete barricade going to offer protection from future tsunamis? Why Japan must build a tsunami wall? The northeast coast of Japan has been living in a state of constant vigilance for decades, being threatened every day with the most destructive forces of nature. The whole international community shares a collective fear as the dangerous alliance of earthquakes and tsunamis continues to define the destiny of this area. Japan lies directly on a geologically active point where four massive tectonic plates, the Pacific, Philippine, Eurasian, and North American plates, are constantly colliding. This results in the Earth's crust running and grinding along this point and registering more than 500 earthquakes every year. Each time this massive Earth crust shifts underneath the ocean floor, the whole floor has been known to move up or down in a matter of seconds due to the massive water displacement created. This Earth displacement creates a massive wall of water known as a tsunami, with walls towering high into the sky, with water levels reaching as high as 30 feet. These walls move at a speed that will take down whatever lies in their pathway, with the force created by water massed up like an ocean current in the nick of time, which could take down anything in its pathway. In those days, small coastal towns were well accustomed to hearing the blaring red alert warning call for help ringing loudly in loudspeakers situated all over their towns. Immediately after this warning, the whole town scampered up the hills instantly as soon as the earth shook underneath them.
There's a reason we use a Japanese word for a catastrophic seismic ocean wave. Japan has had more tsunamis than any place else on Earth. And the massive 9.0 earthquake and the subsequent tsunami.
However, the most devastating occurrence on March 11, 2011, served as the most compelling evidence for that. With a magnitude of 9.0, an earthquake that ranks among the most powerful to have occurred on record, this earthquake broke off a distance of 30 miles at a point where the Earth's crust meets a tectonic plate deep within the Pacific Ocean, with a massive tsunami wave reaching an incredible 50 feet. The massive tsunami wave turned out to destroy 20,000 human lives in its merciless sweep and leveled 120,000 houses and businesses. A catastrophic occurrence broke out at the Daiichi Fukushima nuclear power plant due to this massive earthquake. An earth trembler designed to protect only against walls up to a massive wave height of 26 feet turned out to be utterly defective and completely inappropriate for protection against the great forces brought on by nature. They soon realized that the earthquake was only the first stage of the disaster, as the tsunami was actually the one that brought about the destruction of the communities. Hence, their government decided to undertake the biggest engineering project in history. They built tsunami walls that span almost 250 miles along the coastlines that are highly susceptible to the phenomenon. Every single wall stands 45 to 50 feet above sea level. Its depth reaches as low as 80 feet. It is actually known as the concrete Great Wall, or the Tsunami Wall. The primary intent of constructing these walls is to give the people precious time to vacate when the tsunami comes. The Japanese government spent in excess of $12 billion on these gigantic walls, along with the development of evacuation procedures and regular drills. It is a simple but strongly worded message to the world and to nature. Tsunamis will always come, but the government and the people of Japan will never, ever allow the occurrence of 2011. But could even these colossal walls survive nature's fury again? Engineers had to ask, what secrets lie in the ocean's next surge? Initial research. Extensive lab research began the monumental efforts to build Japan's large tsunami flood defense system through detailed research, with engineers gathering and thoroughly analyzing all data associated with the 2011 tsunami that resulted in thousands of deaths and catastrophic infrastructure damage along the coastline. Consequently, wave tanks along with scale models were developed to replicate the destructive force of these waves, to understand precisely how the large volume of ocean water acted directly against the proposed flood defense structure and how the water overtopped it. In numerous tests, the engineering team incrementally improved critical parameters, including height, thickness, and inclination of the wall, allowing them to design deep foundations that would withstand the enormous forces of the tsunami when they inevitably impacted near the top of the wall. The engineering team completed their design based on peak performance established through multiple simulations of extreme tsunami events. The completed design is a seawall that is between 14 and 15 meters tall, with foundations extending to a depth of 20 to 25 meters below the surface of the ground. A broad trapezoidal base that will channel hydraulic pressure from the wave, and a high-strength steel core that will withstand 100% of the worst possible tsunamis that nature can deliver to the walls of Japan. Construction implementation. Once the design had been determined, the next issue became identifying just where the gigantic wall would be erected. The nearly 400-kilometer-long wall stretches along the Tohoku coast, in the northeast region of the Japanese mainland, known as the Tohoku region, ground zero for the destructive tsunami in 2011. The wall stretches unbroken through the regions of Aomori, Iwate, Miyagi, and Fukushima, making it the longest and hopefully strongest coastal wall in Japanese history. After the precise course was systematically mapped and surveyed, the clearing process was initiated by the removal of thousands of damaged houses and other defective infrastructure that lined the coastline. At the same time, construction sites for the construction of roads that are able to handle heavy machinery and construction materials were established for the massive amount of construction materials that will be needed for the construction process. In addition, platforms that will accommodate the use of cranes for the lifting of construction materials and concrete mix systems that are equipped with advanced technology for the mixing of the concrete will be established. A large extent of the Tohoku coast is prone to various engineering difficulties due to the nature of the soil, which is weak and sandy. Drilling and thorough geologic investigations had to be carried out by experts prior to the application of measures aimed at reinforcing the soil. In the process, concrete or steel piles were erected to a height of 30 meters in areas prone to land erosion. A series of crushed stones with specific grade levels had to be applied, compacted sand under controlled moisture levels, and soil stabilization agents applied. This ensured that a rock-solid soil base was established that could support 15-meter-high walls by countering the powerful force of nature working on the structure. After finishing the soil stabilization process and verifying this through various tests, excavators started digging massive foundation pits, with some areas going over 20 meters below ground level to reach solid bedrock. In areas close to shorelines, construction teams set up complicated temporary retaining walls or cofferdams using steel sheet piling to prevent flooding from seawater or groundwater into excavation areas. After this process, construction teams poured foundational layers of high-strength concrete, followed by embedding dense steel bars into these layers according to calculated spacing. Foundation blocks of up to 50 tons were finally placed to establish an extremely massive footing that prevents the wall from being turned over by the incredible force of powerful waves from strong weather conditions. Above this foundation, large rebar cages were constructed that reached heights of up to 20 stories and corresponded to optimized laboratory designs that had tested well in wave tanks and structural analysis simulations. Sophisticated formwork systems were placed to millimeter accuracy and were then filled by specialized concrete pumps, section by section, while monitoring temperature, slump, and curing conditions of the concrete mixture. Individual blocks several dozen meters in size and requiring hundreds of cubic meters of concrete per block were manufactured this way and then carefully tested for acceptable quality by ultrasonic and visual inspection, and finally connected to neighboring blocks via post-tensioning cables and an epoxy grout to form a single barrier along the entire coastline. On the seaward side, there are specialized concrete structures consisting of tetrapods, delos blocks, and other energy dissipation structures meant for wave breaking and reducing the energy force exerted on the structure. The concrete structures weigh between 10 and 25 tons. The structures have been carefully placed in a multi-tiered manner at the foot of the wall. The strategic arrangement of the concrete structures aims to create turbulence and reduce the wave energy poised to attack the main wall. In other places, there is the use of stepped slopes with calculated angles, sloping surfaces with varying roughness coefficients, and splash protection ledges meant for reducing the water surge. On the landward side, drainage and landscaping systems such as graded soil strata, drainage blankets made of crushed rocks, and complex drainage patterns have been designed and implemented by engineers to ensure the wall does not have pooling rainwater at its back, which could then cause hydrostatic pressures or saturation problems. Many of them have wide paths or viewing roads on them made from hard materials and are wide enough for maintenance vehicles to pass through. In some seaside towns, the seawall has also been designed to form a component of the transportation network and comes equipped with features such as railings, safety fences, access ladders, and even bike paths. It is worth mentioning, however, that the above-described set of principles has been generally followed in the project, but due to the enormous length of the seawall, measuring around 400 kilometers.
This is one of the most important pieces of concrete in Japan. Now, nearly 400 kilometers of tall concrete walls are standing along the coast, designed to weaken strong waves.
There had to be innumerable local variations in the principles of its construction. Every locality was prone to slight variations in the principles of the construction process due to differences in terrains, soil types, depths of the coast, and other factors. But none of these local factors had ever been found to impinge on the integrity of the tsunami barriers. In some of the most vulnerable areas, where a thicker seawall with superior resistance to impacts was required, additional armor units made of precast concrete were applied on top of an existing seawall. These concrete units, which were designed to interlock, were factory-made in a highly controlled manner and then installed in designated positions using special cranes equipped with computer-controlled positioning systems. These concrete units were then fixed together in very close uniform patterns using high-tensile bolts and adhesives, creating what is known as a reinforced armor layer, which greatly improves overall seawall strength and prevents erosion caused by wave actions and sediment being constantly carried in suspension by these wave actions. Once in place, a protective shield is provided to shield against decades of pounding by powerful Pacific Ocean wave actions.
Some call it the Great Wall of Japan, a 400-kilometer-long reinforced concrete shield against tsunami waves, along the country's northeast coast.
even those triggered by typhoons in remote areas. In heavily populated port towns and strategic sea route points, such as Iwaki, Japanese engineers had to work on the complex task of developing these special entry points for enabling commercial and fishing ships to carry on their business as usual, while having tsunami protection fully available and operative. The first major technical innovation introduced in this connection is that of tsunami gates, which comprise massive steel sheets fixed between high-strength concrete towers that stand as high as 40 meters above sea level. In case tsunami warnings are announced by the Japan Meteorological Agency, the steel sheets fall automatically from above, blocking all entry points into a port area and forming vertical barriers that can resist waves up to 10 meters high. In other seaports and harbors, due to either restricted overhead space or aesthetic reasons, Japan has designed bottom-up rising gates. In these types of rising gate designs, the entire gate structure permanently rests flat on the bottom of the sea floor, enabling free flow of boats and vessels through this passageway at all times. As soon as tsunami warning sensors detect warning signals, a highly pressurized hydraulic system raises the gate structure upward, locking it into place through mechanisms that firmly lodge it into fixed side walls, creating an almost invulnerable barrier against attacking tidal waves. Such creative designs can be very useful in seafloors that cannot support overhead space in rising gate designs, and facilitate constant operating functions by boats and vessels at all times of the day and night. The need for such design constructions of seafloors and rated seawalls necessitates the use of highly rust-resistant alloys of steel, maintaining watertight hinges, and bearing systems capable of meeting decades of continuous pressure by seawater and highly erosive sediments of ocean bed soils and corrosive marine conditions. Apart from the physical infrastructure, the project comprised the latest monitoring and maintenance technology, such as embedded sensors, automatic inspection drones, real-time structural health monitoring systems, and integrated emergency response systems. The seawall has monitoring points that detect wave heights, the strength of the structure itself, water levels, and environmental factors, all of which transmit information to centralized control centers where engineers analyze the performance of the wall and program maintenance. The whole infrastructure is established on Japan's nationwide tsunami early warning systems that enable the automatic closure of the gates in case of any menace, and the rapid mobilization of emergency response personnel in case any problem arises. Such a multifaceted approach to disaster prevention infrastructure sets the pace for what can be considered the future of disaster prevention infrastructure that incorporates massive physical infrastructure and advanced technology. But could even the longest, most advanced seawall truly withstand nature's fury when the next colossal tsunami strikes? Results achieved. As a result of the disastrous 2011 Tohoku earthquake and tsunami that took the lives of over 19,000 people and caused enormous damage to Japan's northeastern coastlines, the Japanese government undertook a historic engineering task. This task involved building a tsunami seawall that would extend over 400 kilometers to cover the Tohoku coastline areas known to be most vulnerable to tsunami attacks. After many long years of hard work and dedication, this enormous project of engineering brilliance and achievement has been completed and remains the longest coastline protective structure ever created in Japan's history, and a tremendous accolade to the human spirit and technology's incredible strides against natural forces. The size of this undertaking is evident in the fact that its budget is in excess of $12 billion, symbolizing the determination of the nation to prevent a disaster of such a scale in the future. Over 30,000 specialized professionals were used to support construction activity at its peak. These teams consisted of civil engineers, structural engineers, geotechnical engineers, oceanographers, and construction laborers working closely together to successfully meet the challenges presented by the diverse nature of the terrain and the difficult maritime environment within which they were operating. Thousands of heavy-duty earth-moving machines like high-capacity cranes, deep-sea drilling platforms, and high-capacity concrete pumping units were put to use day and night for a period of 5 to 7 years. The construction activity itself was an engineering feat of modern times, where hundreds of wall panels were constructed simultaneously along the coastline. Each wall panel was prone to its own set of difficulties that needed to be addressed differently, depending upon the local geography and soil conditions of the area. In areas that had soft sediment foundations, deep pile foundations were constructed that reached up to 40 meters for support and stability. In other areas that had rocky foundations, anchored concrete structures that could yield under intense pressures and had steel rebar reinforcements that could give way to intense pressures were constructed. The concrete would also have a special mixture that would withstand the constant attack of seawater and the abrasive effects of sand and debris that would be present in ocean waves. Once implemented, computer simulation and actual testing confirmed that the seawall design was effective in mitigating tsunami force by between 30 and 50%, depending on the wave height and angle. This level of mitigation translates to critical evacuation time that can mean the difference between life and death for coastal dwellers. The seawall design features state-of-the-art technology that includes sloping surfaces that deflect wave energy, overflow channels that deal with excess water flow, and evacuation corridors and shelters spaced along the length of the wall. The protection offered by this massive wall is extended to a number of communities that were wrecked in the massive tsunamis that occurred in 2011. Coastal roads like the Sanriku Expressway, which is a crucial transportation link to the area, have been protected against the impact associated with tsunamis. Fishing ports like Kesanuma and Ofunato, which provide thousands of fishing families with fishing equipment and other necessities for fishing, have been protected. The residential areas in places like Rikuzentakata, where most houses had been swept away due to tsunamis.
The drive into Rikuzentakata is bad enough. The detritus of a place home to 24,000 souls scattered along the roadside, and then you see the town itself.
Have new housing projects constructed with the knowledge that protection against tsunamis will not be a priority. Despite the effectiveness of the seawall, the Japanese government makes it clear that the structure is not completely impermeable. The wall cannot protect the nation against all tsunamis, especially those that result from large earthquakes or those that have irregular patterns. Thus, the 400-kilometer-long seawall is just one of the approaches the nation employs in preparing for disasters. The wall has had a positive effect on the people in the region, making them confident to the extent that they have been able to return to their homes. Looking ahead, the seawall will obviously have to undergo maintenance to keep it effective. The wall is fitted with highly advanced sensor technologies that are able to monitor the levels of stress, corrosion, and overall structural integrity. And this is done on a real-time basis. The effects of climate change, including rising sea levels and the possibility of increased occurrences of extreme weather events, have been factored into the wall's design, and there is provision for increased height and added strength at a later stage. This is not only an engineering feat that has been accomplished, but is also a reflection of Japan's commitment to the safety of its people and the safeguarding of its heritage. But while the seawall guards against nature's fury, how does Japan conquer challenges lurking beneath the ocean's relentless pressure? Other notable projects. Japan's revolutionary undersea tunnel construction technology continues in the line of the most spectacular civil engineering marvels of modern times, and is indeed a testimony to the ingenuity of man versus hostile environmental factors. The working environment is one fully cut off from the surface world, with water pressures that grow up to over 10 atmospheres deep, combined with geological conditions that can change with great fluctuation with every meter excavated. The successful completion of these monumental underwater tunnels is powerful evidence of the extraordinary engineering capability of Japan. Underwater tunnels have evolved in today's global infrastructure landscape, from being engineering curiosities to becoming necessary ingredients of modern transportation networks, with Japan emerging as the unequivocal world leader in this highly specialized field of civil engineering. Travel between Japan's densely populated coastal regions has been revolutionized through strategically positioned undersea tunnels that have become considerably faster, inherently safer, and completely independent of fickle weather conditions that frequently disrupt surface transportation. Such reliability ensures the uninterrupted, steady flow of goods and people to and from the country's bustling port cities, acting as critical nodes in global supply chains. The tunnels are increasingly becoming indispensable economic arteries, substantially raising Japan's international competitiveness while simultaneously opening new frontiers for regional growth, tourism, and cultural exchange hitherto restrained by geographical barriers. But building an underwater tunnel represents one of the most complex engineering tasks in existence and demands many years of preparation, including detailed planning, exhaustive geological surveys using state-of-the-art technology, and precision in design nearing perfection for its safety and long-term feasibility under the extreme pressure conditions of the deep seabed environment. During the initial phase of the project, the subsea floors will be mapped using advanced sonar technologies, remote-operated vehicles, and specialized tools for taking soil rock samples from multiple depths. By performing these seabed surveys of the various material layers under the ocean, we can begin developing a geological profile of the tunnel corridor. Once we have developed a complete geological profile from this stage of the survey, we can assess the geological characteristics of the seabed, determine its capacity to bear loads, identify potential construction hazards, including seismic fault lines or loose sediments, and assess the overall integrity of the proposed tunnel's design as well as its stability. Besides technical considerations, ecological sustainability and environmental protection have emerged as the crucial priorities throughout the design and planning phases of modern underwater tunnel projects in Japan. The project teams have to conduct EIAs that carefully assess the impact of the proposed tunnel on sensitive marine ecosystems in order to make sure that the construction and operation would not harm any endangered species and that it causes minimum disturbance to the natural habitat. For achieving such an environmental objective, noise mitigation measures are fitted during construction, including specialized bubble curtains that dampen underwater sound waves from pile driving or excavation activities. In many instances, the project's team has not only taken proactive measures to address potential impacts, but has also taken steps to enhance the existing environment through the implementation of artificial reefs. These reefs will provide additional habitat for both reef building and pelagic organisms, thus enhancing the overall biodiversity and genetic diversity of the area. Once these extensive surveys and evaluations are completed, construction can commence. One technique that has proven to be effective in constructing underwater tunnels in shallow water and stable seabed conditions is the use of the immersed tube method. This is starting with an innovative on-land prefabrication of enormous reinforced concrete segments, some of the largest single-piece concrete structures ever manufactured. A standard element measures approximately 217 meters in length, much like placing 2 football fields end to end. It weighs over 73,000 metric tons, requiring specialized equipment for handling and extraordinary logistical planning just to move these from the fabrication sites to the launch areas.
Assembling this metal structure is the first step of building the tunnel. It'll be moulded with concrete, and 9 of them will be put together to make a single element.
Manufactured through computer-controlled precision, these tunnel segments allow perfect dimensional alignment and watertight sealing capabilities. With such enormous dimensions, tolerances are measured in mere millimeters. This actual mix of concrete is specially formulated with advanced admixtures and corrosion-resistant reinforcing materials to bear decades of exposure to salt water and extreme pressure conditions. Submerged in their final positions, each segment would carry several internal compartments cleverly designed for specific transportation and maintenance functions. Typically, there would be 2 main chambers fitted for several highway lanes in each direction, 1 dedicated tube for high-speed rail lines, and an additional service corridor that allows access for future maintenance, inspection, and emergency response teams. After these individual segments have been fabricated and extensively tested, they are transported to sea on a complicated flotilla of specialized vessels. These are then carefully lowered into their precisely dredged positions on the seabed. Each segment is then successively joined to its neighbors using sophisticated connection systems. These must maintain perfect alignment despite underwater currents and the immense weight of the structures. In fact, the most critical and technically challenging phase of this entire construction method is with joint connections between segments. These interfaces represent the few failure points through which seawater infiltration could pose catastrophic risks to tunnel safety and longevity. To forestall such catastrophic failures, multiple redundant sealing systems are used, starting with specially formulated rubber gaskets that compress between segments for primary water tightness, supplemented by secondary and tertiary sealing systems capable of maintaining integrity even upon the failure of the primary systems. In parallel, specially designed layers of sand and gravel with ballast materials are carefully laid above and around the finished tunnel structure to balance out extreme buoyancy pressures generated by water pressure at depth. Only when all the connections have been fixed firmly in place, tested for strength, and stabilized by wide-ranging quality control procedures do the temporary end bulkheads get removed, making what is a set of individual concrete tubes one seamless, watertight tunnel that is ready for internal finish and equipment installation. However, this sophisticated immersed tube technique is suitable for sites with comparatively stable seabed conditions and light water currents only, where strongly turbulent water, complex seabed topography, or even significant seismic activity is encountered. The difficulties in positioning with accurate precision and ensuring waterproof integrity under dynamic conditions become such that the immersed tube method cannot be pursued further or considered safe. Once physical construction is complete, the next crucial phase comprises comprehensive safety inspection and operational assessment procedures that comprise perhaps the most extreme test protocols in modern engineering. For many of the newest underwater tunnels being built today, particularly those serving large volumes of city center traffic, multiple levels in both the submerged and underground tunnel sections function to essentially double the carrying capacity of the traffic lanes without extending the structural footprint or requiring additional seabed disturbance. Drivers in the highway lanes can achieve speeds of approximately 60 kilometers per hour here, while every 200 meters, emergency exits and refuge chambers are carefully aligned to assure rapid evacuation in an emergency. Once the entire structure is fully completed, engineers conduct an exhaustive series of tests that include verification of waterproofing integrity under simulated flood conditions, testing for pressure resistance beyond maximum expected loads, comprehensive fire safety assessments using realistic scenarios, heating and ventilation performance evaluations under various weather conditions, and overall monitoring of the structural stability using hundreds of embedded sensors. But the real operational journey of an underwater tunnel begins once it opens up to traffic.
Rates will be a few hundred yen higher during the day when there is more traffic, and a few hundred yen lower when there is less traffic.
And its longevity, safety, and continued reliability are, as a matter of fact, determined by ongoing maintenance. Specialized technical teams periodically inspect every critical system, from the concrete lining and waterproof membranes to the support frames and drainage systems, using innovative non-destructive testing methods to ensure no deformation, cracking, or material degradation sets in with time. Hundreds of sophisticated sensors installed along the tunnel continuously monitor crucial parameters such as internal and external pressure, temperature fluctuations, humidity levels, and vibration patterns, sending real-time data streams to central control rooms where advanced artificial intelligence systems can detect even the slightest indications of structural fatigue or potential problems long before they would be discernible by human inspectors. Parallel to these high-tech monitoring systems, periodic cleaning and sediment removal operations are conducted with the assistance of specially designed maintenance vehicles fitted out with high-pressure water jets and powerful suction systems that forestall blockages in tunnel drainage systems and hazardous conditions. All these, a sophisticated blend of advanced sensor technology, along with predictive maintenance algorithms and precision manual inspection routines, enable today's underwater tunnels to operate safely, efficiently, and sustainably for a very long period of time. Thank you for watching today's video. We hope you liked it, and if so, be sure to leave a thumbs up and don't forget to subscribe.